Hi everyone, my name is Zach, and today we're going to talk about the simplest problem I think SpaceX is running into while defining the primary structure of Starship. In my opinion, the challenge Starship structural designers face is stability-related behavior stemming from its material selection, which will result in an extremely high dry mass and an extremely large structural coefficient. I don't work there, and I don't mean to insult anybody's work here, so this is largely just an academic exercise. I haven't seen anybody talk about this in a way I think captures the nuance of the issue, so I figured it'd be a short and fun video. In general, density is the most powerful term in the equation for weight savings. This may sound obvious, but it's not. A stronger or stiffer material has its stiffness or strength raised to an exponent less than 1 in the equations for stability, so the typical algebraic computation of weight savings which ignore buckling will lead you down a false path. If you compare the stiffness to density ratio for various aerospace metals, you'll see an almost serendipitous equality between them, and this could lead you to choose the material you think is cheapest or easier to work with. But as I showed before, it's not that simple. For example, the F-8 Crusader used magnesium extensively, even though magnesium is very annoying to work with. And it's not just because of the properties of magnesium, but because of what those properties let you do. Any competent structural engineer knows that changing materials also changes the form that the structure wishes to take. A magnesium and aluminum skin assembly, both of equal weight and strength, could differ drastically in their ease of construction, because the aluminum skin might need stiffeners, while the magnesium skin might not. A steel structure may wish to be a spiderweb of small members to prevent local buckling, whereas a wooden structure can be so globally thick without incurring a weight penalty that global buckling may be the only concern. In this way, you can envision a design using a high-density and high-stiffness material, like steel, to be a balancing act of many different stability-related failure modes. To be more specific, we can work an example, a very famous and fast example. The plate buckling equation, shown here, penalizes thickness and width equally. Let's design a shipping container, one wood and one steel. If you design them both the same way, you'd see that the steel container would need to be heavier to carry the same load on top of it. Assuming a 72-inch square plate of a crate made of 1-inch thick plywood to start with. For this specific example, because the width of the plate is the same, and the densities differ by a factor of 20 and the stiffness is by a factor of 29, the two plates of the same weight would differ in strength by a factor of 309 in favor of the wood. The 1-inch thick plywood plate is just as heavy as a steel plate that's 48 thousandths of an inch thick, but carries 309 times more load before it buckles. The solution to this problem shouldn't surprise you. It's to interrupt the steel plate into many smaller strips, and when you do that, you see the steel example becomes far more efficient than it was before. If you break the plate into a corrugated section with a net height of 1 inch made up of 24-gauge steel, you'll have a section with 4 times the linear buckling resistance of the wooden design at approximately the same weight, 71 pounds instead of 72.6 pounds for the wooden design. But now you've won one design trait at the cost of another. You need to check that the global stiffness isn't worse than that of the wood by comparing the modulus of elasticity times the second moment of area to the wooden design to ensure you haven't compromised the global buckling at the cost of the local. But this is all just one example for a single structural feature. Imagine this level of tailoring for every web and flange on the entire vehicle, and you can imagine the degree of work needed to really tune a vehicle's structural behavior. Circling back to Starship, I think the architecture is doing a lot of work to mitigate the shortcomings of the material selection. By catching the booster from the top, it can avoid loading a hot and empty cylinder structure in compression, which means you get to write margins for a lot of the structure to the high tensile yield allowable, rather than the lower compressive yield allowable. Additionally, by pressurizing the vehicle's primary structure with a cryogen, they can place the entire primary structure in tension rather than compression on ascent, which can ward off buckling so long as you comply with a couple of load conditions, the most important of which, in my opinion, is that the combined hoop stress and compressive or in-plane stress doesn't get too close to the yield stress of the material. And because this material gets far stronger in the cryogenic regime, this seems like a really good way to capitalize on the benefits of the material selection. Starship, on the other hand, will encounter all kinds of challenges due to its material selection, especially on descent. If the plan is to actually send this vehicle to Mars, where it will have to land on legs from its bottom, it will need to be placing its entire primary structure in compression, and under a transient load that I believe will be closer to a shock load than a load that could be represented quasi-statically. I think holding some degree of internal pressurization can help with this. But if you look at the plastic buckling or crippling behavior of this 304 stainless at high temperatures, you're in for a wild time. Being courteous and assuming you're allowed to damage the structure irreparably on landing, which is what crippling means, can help the story drastically. I think they will try and make it so the first starships to land on Mars won't be expected to fly again. That way they'll be able to use their own crippling structure as an impact attenuator until they manage to build a catching tower or whatever their plan is. From a thermal structures point of view, I have to imagine they want to use their higher temperature capacity of stainless steel and allow more heat to transmit to the primary structure than, for example, Space Shuttle may have done. But doing that reveals another particularly nasty problem, and that's the very low thermal conductivity of 304. Starship appears to be using hat sections longitudinally in order to allow hoop expansion of the tank and as the primary load carrier. If they're cranked up to the maximum thickness of the sheet and strip stock of the AMS specs sourced by MMPDS, they're stuck at 187 thousandths of an inch thick. So if both the skins and the sections are that, the only way to get more cross-section in there is to pack more detailed stiffeners in there. And if they're forming these at full hardness, then the bend radius allowables will restrict the geometry of the stiffeners. And I think that's what's going on here. It's probably why they're knocking holes in the webs on the innermost side. In essence, I think they're stuck with a fixed height of stiffener. And if you're allowing the OML to get hot, this is not quite the geometry that you want. If the outer flanges and skin try to expand and the inner flange stays cold, then you're going to get all kinds of interesting thermal buckling going on, and extremely high compressive forces on the inside flange, while it's being loaded in bending or compression, of course, which is not only stiffer because it's colder and therefore taking more load, but is also the compressed side of a beam undergoing thermal bending, which needs to be resisted by the internal pressure, which actually gets worse the higher the moment of inertia of the stiffener is. So, unless I'm not understanding the situation here, which is a very strong possibility, I think the TPS to primary structure demarcation line is going to be limited to temperatures comparable to that seen on the space shuttle, which, in my opinion, squanders a really good use for the stainless steel. It's a really unique case of stainless steel in aerostructures, Starship is. Stainless steels have been in use on flying boats and aircraft since at least the 1920s, and on rockets since Atlas V gave up on steel balloon structures and transitioned to aluminum isogrid. I wouldn't be surprised if such a change happened in the future to either aluminum or a superalloy like Inconel, because if they don't do that, and if they want to get weighed out, they're going to need to make this thing look a lot more different than it does now, or they'll just make the engines work better. That seems to have worked for them so far.